Hello, and welcome to the worksheet walkthrough for worksheet number 6. So this worksheet is a pretty involved one, actually. It has a lot of stuff on weighted quick unions. It has a lot of stuff on runtime. And this weighted quick union problem in its own right is quite a big one, actually. It's deceptively big. But I think that if you can do this problem, you can do pretty much any weighted quick union problem. This is a great little data structure that we like to teach towards the start of the data structure portion of this class, because it is fairly simple compared to some of the other data structures we're going to be looking at. It's implemented entirely in an array. And one thing that's cool about it too is that the kind of representation of the actual data structure does not match the actual implementation of it, right? Okay, so what is a weighted quick union? This is just a little bit of a recap. I'm sure you can watch the lecture or go back to lab for more information. But basically, a weighted quick union is a data structure that has two operations, connect and find. And basically what we're going to do is we're going to connect a bunch of sets and just tell if two things are the same set, right? You could think of reasons you might want to do this. You have a bunch of different sets of objects. Maybe you have, a bunch of different sets which represent students in a class. You connect the ones that are in the same class together, and then you want to say, hey, is student A in the same class as student B? You can just tell if they are or not, right? So let's say that we have that example. Let's say that we have 6 students in a school, and there are 2 classes in that school. Let's say that these 3 students are in one class and these 3 students are in another. So basically what we would do is we would use a bunch of connect operations to connect the students, right? So you can see here now with the arrows that I drew that 2 and 1 are connected to 0 and 3 and 4 are connected to 5. And then we could say, okay, are student 2 and 1 in the same class? And we can tell because if we follow the arrows all the way up, they both match 0. And if we say something like, are students 2 and 3 in the same class? We can say they aren't because we follow their arrows all the way up till we can't follow them anymore. We see their 0, we see their 5, they're different, therefore they're not in the same class. So that's an example here of how you might use a weighted quick union. It's all about set membership. Another thing you might notice is you say, okay, well, that's great that you say students are in the same class, but these aren't student objects. These are just, numbers, right? 0, 1, 2, 3, 4. These aren't actual objects. And you'd be right. So normally what you would do is you would have an auxiliary data structure. So if you wanted to make this basically with the student example I just said, you would perhaps have like a map that maps number 0 to a student object and the number 2 to a student object. That way you would say, okay, are 2 students in the same thing? You would check their numbers, you would see if their numbers are the same, and if they are, the students are. That's basically how you would implement this in real life. Okay. So we see here that, oh, actually one more important note about this too, is that the kind of top member of the set, the element that has no parent, we often refer to as the face of the set, and it's arbitrary, right? So remember when I was saying, okay, are 2 and 3 in the same set? I looked at their parents, I found that the faces of their respective sets were 0 and 5. I said 0 and 5 are different, so they're not. It doesn't matter that there's 0 and 5. We could do the same exact thing if we had 2 sets that look like this, where 2 is the face of one set and 3 is the face of another set. All it means is that it is the topmost element of the set. So it doesn't matter which element it is because we don't care about numbering the sets or anything. We only care about saying, hey, here's one element, here's another element, are they in the same set? And we can do that by looking at the faces of the sets. Okay, so this is all cool and everything, but you can imagine if you wanted to implement this data structure in code in real life, you would probably have to do something fairly complicated, right? You would probably have to define some kind of like node class or something to hold these. You would have to have, each node class would have to have like a parent value, et cetera, et cetera. But we don't actually need to do any of that because we can implement this all with a simple array. So let me have an array here. Here's an array with indexes 0 to 5. Each one matches up to one of the kind of nodes that we drew on top. And let's see how we would basically display this tree diagram here in terms of an array. So remember, what matters here, basically? What matters is the parent of a given element. So in this case, 1's parent is 0. So in our array, how we are going to represent that is we are going to go to index 1, right? Index 1 is correlated with the actual number 1. and we are just going to put 0 inside index 1. So we can say that its parent is 0, right? So basically what is inside the array represents your parent. Similarly, 0's parent is 2. So we're going to go to index 0 and put 2 in here, right? And let's fill that out for the other things. So 4's parent is 5, 5's parent is 3. And now we come to this a little issue here, right? What is 2's parent and what is 3's parent? Well, we could just say 2's parent is 2, and we could say 3's parent is 3, but we don't want to do that because basically what we're going to want to do is we're going to want to follow up to the parent, but we want to do something different once we reach the parent. Remember, when we were doing find operations, we were saying, oh, is 4 and 1 in the same set? We went up and we found the face of the set, and then once we had the face, we compared the faces. So we want to treat this differently. So all I'm going to do is I'm going to say -1, right? Because we're only using positive numbers otherwise, so we can use negative numbers here. And basically, if the thing at your index is -1, that means that you are the face of a set, right? So let's do the same thing we did before, but now in terms of this array. Let's say we want to check if 0 and 4 are in the same set. So basically, we first find the face of 0. So to do that, we go to index 2. We go to index 2. We see that index 2 has a -1 in its index. That means 2 is the face of that set. Great. Then we do the same thing for 4. We go to 4. We see 4's parent is 5. We go to 5. We see 5's parent is 3. We go to 3. We see 3 is the face of a set. Great. So now we found that 2 and 3 are the numbers we're actually comparing. We compare them. They're not the same. Therefore, they're not in the same set. If that was all quite speedy, please watch the lecture again, because I'm sure they explained it in more detail there too. Okay, one final note about how we're going to be doing this is notice that we've just said the set of two things is going to be 1 or -1. One thing that we're going to do that's actually a little optimization, it's going to help us out, is we're going to keep track of how big each set is in addition to the fact that this is the face, right? So before I said, okay, we can use -1 to indicate where the head of a set because the negative numbers are not being used here, but other negative numbers are not being used in this implementation either, right? There's no -2, -3, -4. So what we're going to do is we're going to basically encode the size of our set as the negative value. So basically 2, how many things are in the set whose face is 2? There are 3 things total, right? So we're going to put -3 in index 2. And same thing with 3, because 3 is also a set of size 3, right? Okay, so what does all this mean? Basically what it means is that, in summary, basically, every index represents an element of the set, every index in the array. The contents of that index means something else. So if the contents of a given index is a positive number, it means that that number is the parent of that particular element. If the contents of an index is negative, negative means that is a face, right? The fact it's negative means it's a face, and then the absolute value of that negative is the size of the set. So here we can see -2 is face of a set because there's a negative, and how big is that set? It's size 3 because there is a 3. Why do we want to do that? It's because eventually, once we start doing this problem, when we connect bigger sets, we're going to want to connect them based off their size. So let's look at, let's make this example a little bit bigger. Let's just say that there was also a 6, and let's say it's pointing at 5 here, right? So 6 parent is 5. That means that the size of 3 is going to be 4. I changed the example just for demonstrative purposes, but it's the same thing, right? I just added a new element. Okay, let's say that we want to connect 2 sets. Before, I was just connecting single numbers to sets, but let's say that I want to connect, now let's say I want to connect the set containing 5 and the set containing 0, right? We're not just connecting a number like this, because when I say connect 2 sets, I want to connect the sets, not just the elements, not just the individual elements, right? So if I want to connect 5 and 0, basically, I need to find the face of 5, I need to find the face of 0, and then I need to connect those 2 things together, right? So let's find the face of 5 and the face of 0. So the face of 5, we just follow up the pointers, right? We see, okay, inside index 5 is 3, which is this number, and we see that 3 is the face of its set, and its size -4. So we know we're going to connect this number. And let's just say that we want to connect. Now we want to find the face of 0. So we're going to do the same thing. We're going to look up index 0. Whoops. Look up index 0. Index 0's parent is 2, which is this number. 2 is the face of its set, which is -3. So now we know that we want to connect -2 and -3. But here's the question. Do we want to connect 2 to 3 or do we want to connect 3 to 2? In this class, with weighted quick unions, we're always going to connect the smaller set to the larger set, right? And that's where it becomes useful to keep track of the set size in addition to whether or not you're a face. Because now it's really easy. We don't have to count every single element of the set, right? Imagine how much of a nightmare it would be starting at 5 to count how many elements are in this set, because you can't just follow up the parents. You'd also have to figure out 6 and 4, right? You can't follow pointers backwards, only forwards. So it would be a linear operation, and it would be really terrible for runtime. But because we've encoded the negative value of the set of size into our array, we know instantly once we get to 3, once we get to the face, that the size of the set is -4. So we're going to connect the smaller set to the bigger set. That means we're going to connect 2 to 3 like this. And then this is a really easy thing to update in the array also, because now we just combine, we add -4 and -3 together. So 3 is the new face of the set, so it has size 7 because there are now 7 elements in it. And 2's parent is 3, right? So we only have to change those 2 numbers. That's basically a weighted quick union in a nutshell. If that went really fast, I would encourage you to please watch the lecture again or reread the lab where we worked on this today. I hope that makes sense, though, if you just didn't quite get it and if you needed a visual. But now we basically have to move on to the actual problem. Okay, so this problem is basically just asking you to connect and find a bunch of elements and just draw a picture, basically do what we just did, but following these steps to make sure you can do it. So we're going to do it. We're going to do it with a weighted quick union without path compression first, and then I will show you how to do it with path compression. If you don't know what it is, don't worry about it right now. We'll talk about it later. Okay, so basically we want to do connect and find, and we're following all the standard rules of weighted quick union, right? We're going to break ties in size by choosing the smaller integer to be the root. What is a tie? A tie is when we're trying to combine 2 sets of the same size. We just put the bigger one as a child of the smaller one, right? Just to arbitrarily break things. Okay, so let's see what we have here. First of all, I'm going to see that there are 9 elements total, 0 through 8. And so I'm going to draw both a tree representation and an array representation, so you can see what both are doing at the same time. Okay, this at the bottom is our array, at top is the tree. So when we start with a weighted quick union, every single element is in its own set, right? Nothing is connected yet. And we're going to represent that in our array with all -1s. Why -1s? Well, remember again, negative means you're the face of a set. And currently, since all of these elements are not together in any sets, they're all the face of their own set, they should all have a -1. And it's -1 because these are all sets of size 1, right? There are no parents anywhere. Sometimes you'll see this drawn like this in terms of like nodes, little circles around them. I'm not going to do that just because it clutters the diagram a little bit. Okay. So we have this. So let's start connecting things. So the first thing we want to do is we want to connect the set containing 2 and the set containing 3. I'm going to try to use very specific terminology here because remember, we're not necessarily connecting 2 and 3. We're connecting the set which contains 2 and the set which contains 3, because we don't care about who the face of the set is. We just care, are you in the set or are you not in the set, right? This whole kind of parent thing and face thing is really just like an illusion. Okay, so what are the steps? The first step is we're going to find the face of 2 and the face of 3. And then we are going to connect the smaller set to the larger set and update any parameters we need to. So let's find the face of 2 and the face of 3. How do we do that? We go to their indices, their respective indices in our array. We see they're both the faces of their own set, which makes sense because this is the first set. This is the first connect operation, so everything in its own set. And we see that they're the same size, right? They're both size 1 sets because they don't contain anything else. So we're going to connect the bigger number to the smaller number, which means we're going to connect 2 to 3 like that. And let's update our things here. 2 now is the face of a set, and a face of a set with 2 things in it because 3 is pointing to it, and 3's parent is now 2. So that's how we did it so far. And again, remember, this is the tree representation. This is the one that's probably easier for you to understand in your head, is the visual representation. And this array is what is actually in your computer. So remember, two different representations, but this one is the actually concrete implementation. Okay, let's connect some more elements. Now we want to connect 1 to 2. Okay, so we need to find the face of 1 and the face of 2. So we go to 1, we see that it is the face of its own set. It is the face of a set. Now we go to 2, and we see, okay, 2 is the face of a set, right? It has no parent. But 2 is the bigger set here, right? 1 is a set of size 1, 2 is a set of size 2. So we want to connect 1 to 2 just like that. And now let's update our numbers again. 1 is going to be the child of 2. And 2 is now a set of size 3. It's just slowly building numbers so far. 5 and 7. Okay. So basically, we're going to look at 5. We're going to look at 7. We're going to see basically they're both on their own. They're in their own set. So this is tied again, 2 sets of size 1. So we're going to connect 7 to 5 because we're connecting to the bigger to the smaller. So 5 is now -2, and 7 is now the child of 5. Great. 8 and 4, moving right along. Same thing here as before. 8 and 4 are both on their own, so we're going to connect the bigger number to the smaller number and update our variables. 4 is the new face of the set, so it's -2, and 8 is now the child of 4. This is a good place to stop and check your understanding so far about basic set connections, because so far, basically, everything we've connected has been the face of its own set, which is going to start to change once we look at the next one. Okay, so now we want to connect 7 and 2. So what we're going to do is we're going to go to 7, but we want to find the face of 7. We're going to see that 7's parent is 5, so 7 itself is not the face. So then we're going to go to index 5, and we're going to see 5 is negative. Okay, that means 5 is the face of the set, right? So see how we did that. We went to the index, we saw the thing at the index, then we went to that index and saw the thing at that index. And we can continue that chain as long as we want. And see how it's mirrored up here in the diagram. If we start at 7, we see 7 has a parent. Its parent is 5. 5 does not have a parent because it's the face of the set. Okay, so we're connecting 7 and 2. But remember, we're actually connecting 5 because we're connecting the set that 7 is in, which is actually going to be the set whose face is 5. Okay, now we look at 2. 2, as we know, is the face of its own set. It's a set of size -3, or of size 3, sorry. We're going to connect the smaller set to the bigger set, which means we're going to connect 5. Oops. Let me try to not erase that entire diagram as I do that. We're going to connect 5 to 2 because 2 is the bigger set. Okay, and now let's update our variables again. That seems like a big operation, but it's actually a relatively simple update. We just add together -2 and -3, which are the sizes of the sets we just did, throw them in 2 because 2 is the face of the set, and now 5's parent is 2. Right? This is what it looks like so far. Okay, all this stuff has been happening internally. The user doesn't actually receive any output from this. Now what the user is going to do is they're going to run a find operation in 3. What find is going to do is it's going to tell us what set does 3 belong to. In other words, what is the face of the set that 3 belongs to? So we can just look here. 3 is pointing at 2. 2 has no parent, so 2 is the face. We can also do it via the array. 3, its parent is 2. We go to 2, its parent is negative. So this is just going to return 2. Okay. Keep in mind, if we called find on 0, it would return 0. If we called find on 7, it would also return 2. If we called find on 8, it would return 4, right? It's just follow the arrows up until you can follow them no longer. And hopefully you can see the kind of equivalent operation we do on the array. Just look at what is inside your index, go to that index, et cetera, until you hit a negative number. Okay, now we're going to connect 0 and 6. 0 and 6 are previously unconnected. We see they both have -1s in the array, but we see they have no parents in our tree representation. So we're going to connect 6 to 0, because remember, the bigger one is connecting to the smaller one. It's an ugly looking 6. I'm going to change that to, so 6 is connected to 0. 0 is now size -2. Great. Next one, 6 and 4. Okay, find the face of 6. The face of 6 we see here is 0. Find the face of 4. The face of 4 is itself. So these are both size 2 sets, right? The set headed by 0 and the set headed by 4 are both size 2 sets. So we're going to connect the bigger number to the smaller number. We're going to connect 4 to 0. just like that. This is the same thing we were doing, by the way, when we were connecting sets of size 1, right? Previously unconnected sets. They were the same size, so we say we're going to pick the smaller one and connect it to the bigger number and connect to the smaller number. Same thing here, it's just that the numbers we're connecting in this case are the faces of their respective sets, right? Okay, now last connect operation is 6 and 3. So we need to find the face of 6, we need to find the face of 3. So just looking at this diagram, I can see that the face of 6 is going to be 0. 6 goes up to 0, 0 has no parents. So we're going to want to connect 0. And then we want to connect the parent of 3, or the face of 3. The face of 3 is 2, because we just follow up the same way. So we're going to connect the set containing 6 and the set containing 3, which is the set that has a face of 0 and the set that has a face of 2. We see here, one is a size 4 set, one is a size 5 set. So we're going to connect this smaller size set to the bigger size set, which means we're going to connect 0 to 2 like that. That means that 2 now has a total size of -9 because we just added the 4 elements of 0 into the set headed by 2 or faced by 2. And then 0 is now pointing at 2. Okay, lots of arrows going everywhere, but that's the end of the connect operations. Now we can do 2 find operations here. So what are our find operations going to do? If we find on 8, look what's going to happen. We're going to start at 8, then we're going to go to 4. We're going to its parent of 0, its parent of 2. 2 has no parent. Therefore, this is going to be 2. We can do the same thing in the array. If we start at 8 in the array, we see that 4 is the thing at index 8. We go to index 4. We see that 0 is the thing at index 4. We go to 0. We see that 2 is the thing at index 0. Then we go to 2. We see it has a negative number, so we know 2 is the face of the set. All of that is a big fancy way of saying the answer to this one is 2. Now let's look at 6. I'm not going to draw it all out again, but hopefully you can see 6's parent is 0, 0's parent is 2. So again, 2. And also, if you kind of zoom out and look at the macro picture here, that kind of makes sense because notice, look at this array. Remember, an element is negative when, an element is negative when it is the face of a set, when that index is the face of a set. There's only one negative element here at this point, which means that I can tell you right away that every element belongs to set 2 because it's the only one that's a face. And if it's the only one that's a face, there must be no independent sets, but there must be no other sets. Similarly, there's a lot of arrows up here, but if you look at them, what you'll find is that all of these eventually lead back up to 2, because that's just the way we connected everything. Okay, that's basically how you would do this problem. This is a rather complicated one, but if you can do this one, you can do any weighted quick union problem again. A couple notes here, now that we finished. So we were always connecting the faces of 2 different sets, right? For example, when we connected the set containing 4 and the set containing 0, right? That I believe was this one, right? 6 and 4. Why do we have to connect the faces? Why couldn't we just, put an arrow from 6 to 4? And the reason is because we want to keep a chain going, right? If we want to connect, let's say we have a different picture. If we want to connect, for example, the set containing 0 and the set containing 3, we can't just do this because then 1 will not be able to get to 3, right? We want to be able to get all the way to 3 from any number inside that set because remember, we don't care about individual elements, we care about set membership. Okay, that's basically why that works. Now we're going to repeat this process, but we're going to do it with path compression. What is path compression? It's another optimization to weighted quick union that's going to make things run more smoothly. So, for example, something you may have seen in the previous one, let me actually just get it back up here, is if we wanted to find the set that contains 8, it's a pretty long process, right? Because we have to go to 8, then we have to go to 4, then we have to go to 0, then we have to go to 2, right? We have to follow this whole chain up. And you could probably imagine a situation where you have hundreds or thousands or n, basically, nodes, and you would have to travel through like n nodes just to find what set you're in. But remember, we only care about set membership. We don't care about the individual elements in the set, right? If I run find on 8, I want you to tell me it's a member of the set whose face is 2. I don't care that 8's parent is 4 or 0. I only care ultimately what is its kind of furthest back ancestor, right? In this case, 2. So in other words, it would be equally valid if instead of 8 pointing at 4, 8 just pointed at 2 directly. It would also be equally valid if instead of 4 pointing at 0 pointing at 2, 4 just pointing at 2 directly, right? So that's basically the idea of quick find. Every time we run a find, what we're going to do is we're going to keep track of all the individual elements we saw along the way, and we're going to rebind them ultimately to have a parent of the face at the end, right? So that means that if we do a quick find on 8, whoops, that was an erase. We're going to see 8, we're going to see 4, we're going to see 0. All of these numbers are going to be pointing at 2 after we do it. Okay, let's do it in a little bit more detail with the actual code and everything on display. Okay, so these first 5 operations are not going to be any different because when we are doing, when we're adding path compression only affects find operations. So before we hit that first find, nothing's going to be any different. Okay, so basically I've reset the diagram now to where it would be after I complete these first 5 operations. If you want to try doing it on your own, go for it, or just watch the earlier part of this video again if you're still confused. So now basically what we're going to do is we're going to start running find operations. So find is going to be the same thing we did before, right? Where we just basically start at whatever number we're finding and go all the way up to the face of the set. But now what we're going to do is we're going to keep track of every number we find along the way. And at the end of our find operation, we're going to rebind the parents of all the numbers we found on the path up to the face. So in this case, nothing actually changes because we're going to look at 3. So I'm going to underline 3 here. 3's parent is 2. So we're going to return 2, just as before. And then we're going to rebind 3's parent to be 2. But 3's parent is already 2, so not much has changed here. By the way, find is not going to change the correctness of this. It's only going to change the runtime of this data structure. So we already know, right, if you remember that we found 2 on all of these when we did it the first way, it's still going to be 2 on all of these. It's just that the data structure underlying it is going to look a little different at the end of this. Okay, so let's connect 0 and 6 again. So we look at the second thing, 0, 0 is on its own, 6 is on its own, so we're going to connect 6 to 0. I'm going to blow through this all pretty quickly because I already did it. Then we're going to connect 6 to 4. 6's face is 0. 4's face is 4. They're the same size, so 4 is going to be pointing at 0 like that. So we get -4 and we get 0. And then we are going to connect 6 to 3. 6's face is 0. 3's face is 2. So we're going to connect 0 to 2 like that. So 0 is going to be pointing up at 2. And then 2 is going to be -9. Okay, so now we are at where we finished before, right? This is the same as we did before, but the find operations are going to be a little different. So now let's find 8. When we find 8, what we're going to do is we're going to mark everything we find on the way. So first thing we're going to do is we're going to start at 8, and then 8's parent is 4, 4's parent is 0, oops, 0's parent is 2. So 2 is ultimately where we're ending up, right? So we're going to return 2. However, we're not done here because, again, remember, we don't care that 8 is pointing at 4. We only care that 8 ultimately points at 0. So every number I underlined, which is basically a number that we found in the path, we're going to rebind its parent to be 2. So 8 is no longer pointing at 4. 8 is now pointing at 2. 4 is no longer pointing at 0. It is pointing at 2. 0, its parent is going to be rebound to 2, but it already is 2. And 2, we're not going to rebind because it's the face of the set, right? So see how this does not impact the correctness of what we've done so far, right? Because 8 ultimately still points at 2. 4 ultimately still points at 2. We've just changed some of those intermediary pointers along the way. So now if we ever call find on 8 again, we can go straight to 2 instead of having to go through 4 and 0, et cetera, et cetera, et cetera. Okay, now let's find 6. Okay, so we start at 6. 6 is pointing at 0, and 0 is pointing at 2. So we return 2 because 2 is ultimately going to be the result of find. And then we rebind 6 to be pointing directly at 2. We rebind 0 to be pointing directly at 2, but it already is, and we don't need to rebind 2 because 2 is the face of the set. So this is what it's going to look like after path compression. Also, I forgot right here that I need to update the actual elements in the array too. But basically what's happening is our array is going to end up looking something like this at the end. Notice here that almost all the elements are pointing directly to, because remember, they may have had parents before, but we rewound those parents to be 2. Also notice that 7 is still pointing at 5, which is pointing at 2. Why did we not optimize 7? It's because we never ran find on 7. If we were to run find on 7, we would, find that 7 goes to 5 goes to 2, and then we would rebind 7 to 2. But we never did, right? We don't actually compress these paths until we run the find operation. So that's why that's not done yet. That's how you do that. That's the hard part of this question. Okay. However, there is a bit of a conceptual thing afterwards, which we can go over too. Basically, you're being asked about 3 different operations or 3 different data structures and the runtime of connect and is connected on both of them, or on all 3 of them. Okay, so we have quick find, quick union, and weighted quick union. The first 2 problems, we were just doing weighted quick union, one with and one without path compression. Weighted quick union is kind of an amalgamation. It's kind of the greatest hits of both quick find and quick union, which are similar data structures, but are not quite optimized, right? So all these data structures are doing the same thing. Fundamentally, the problem is the same, is we have a bunch of things, they're in different sets. We want to tell if things are in the same set or in different sets. And we're going to approach it the same way with an array and with faces and connecting the faces. It's just the individual rules for how we're going to do that are going to be a little bit different for each version of this data structure. And that's going to affect the runtime that it actually takes to do a particular operation. Okay, so quick find. Quick find is very similar to what we were just doing. It's very similar to path compression, but it's less efficient basically. So what quick find is going to do is, let's say that we had some sets that look like, let's say we had some sets that look like this, basically. And we want to find if 4 and 2 are in the same set. We're going to do the same thing that we were doing before, right? Where we just say, okay, let's look at the face of 4. The face of 4 is 4. Let's look at the face of 2. Oops. 2, it's 3. 3 is not 4. It's not going to be the same thing. The difference is when we actually are going to do connects. So when we connect things, we're going to basically do path compression, but we're going to do it live. We're not going to do it on find operations. We're going to do it the moment we add something, right? Keep in mind, in the previous problem, we didn't do path compression until we did a find. So let's say that I want to connect 4 and 2. In this diagram, I'm going to do the same thing we did before, right? I'm going to find the face of 4, find the face of 2, connect the smaller set to the bigger set. Sure. Okay. Now, let's say that I want to connect 2 and 0. Okay, this is where things are going to be a little bit different. So in our weighted quick union, what we would do is we'd find the faces of the sets, which is 0 and 3, and we connect it just like this. That's not what we're going to do in a quick find, because in quick find, we don't really care how long the union takes. We're trying to optimize the find. It is quick find, not quick union, right? So basically what we're going to do is we're just going to scan through and we're going to find, let's say we're trying to connect 2 and 0 again. We're going to find every element that belongs to set 2, every element that belongs to set 0, and we're going to pick a face and we're going to bind them all to that face. So let's say we're connecting this set to this set, the bigger set to the smaller set. It doesn't matter in this one also. We're not doing it by size. What we're going to do is we're going to change 2's pointer to be pointing at 1. We're going to change 3's pointer to point at 1. We're going to change 4's pointer to point at 1. Another thing to note, in quick union and quick find, we're not connecting the bigger set to the smaller set. We're just connecting them arbitrarily, right? Notice this is a weighted quick union. That's what the W means. That means we're connecting the smaller set to the bigger set. Here, it doesn't matter. It could be either way. Okay, so that's basically what we're going to do. So you see that we're going to end up with a result really similar to our weighted quick union with path compression we just did, but we're doing the path compression right out, right? So now let's talk about how long it actually takes to do this kind of operation. So how long does it take to connect something? Well, to connect something, it actually takes linear time, right? It takes n time. Because what you saw here, right, is you saw we had a set of size 2 and a set of size 3. We had to go through the entire array, basically, figure out which element belonged to each set, and then connect it all to one set. So we had to go through everything, which usually takes n time. Another way to think of it is, let's say you had two sets. One had n elements, one had another one had n elements. Two sets with n elements in it, and you want to connect the two sets. You're going to have to change every single pointer from one of the set to be pointing to an element in the other set, right? Which means you're going to have to change n pointers. So in other words, connect is going to take at an upper limit at most n time. It doesn't necessarily always take n time. Remember that first operation we did where we connected 4 to 3, that did not take n time, but it is possible for it to take n time, which is why we say O of n. However, is connected is going to be really, really fast because look, if we want to check is connected now, we only have to go up one thing, right? If we want to check if 2 and 4 are connected, we can just look up one element to the face, right? If we want to check if 3 and 0 are connected, we can just look up one element to the face, right? In other words, we never have to follow any long chains because we did all of this kind of path compression live. We only ever have to look up one node to tell something's the face of something. So that means that it will take constant time always for us to actually check if two things are connected, if two things are in the same set. So that's the advantage. Remember, this is quick find, so it makes sense that to find things is really fast, but to actually connect them is really slow. Quick union over here is kind of the opposite. So in quick union, we are trying to optimize how quickly we union things, but we don't care how long it takes to actually find them. So let's set up this previous example that we just had, 0 and 1 and 2 and 3 and 4. So in quick union, we're going to do the opposite. We're going to basically connect the faces of two sets, and that's pretty much it. Right? So let's say that I want to connect 4 and 2. I'm going to find the faces of those sets, and I'm going to connect one to the other. It doesn't matter which. So if I want to connect 4 and 2, we'll find that the face of 2 is 3, face of 4 is 4. I'm going to connect one to the other. You might connect 4 to 3, you might connect 3 to 4. It doesn't matter. We're not doing it based off size. It's just random here. You can see hopefully why it would be inefficient to connect the bigger one to the smaller one, because now there's a longer path to traverse up if we want to find the face of the set. But that's how a quick union works. Now let's connect, let's say 1 and 2. Okay, so first, as usual, we're going to find the faces of these respective sets, which is going to be 4 and 1. And let's just say we're going to connect 4 to 1, right? We're just going to do like that. We're just going to connect the two faces. We're not going to reorder any of the elements. We're not going to do any path compression. We just connect the two faces. And the only difference here between just a regular quick union and a weighted quick union is that we are not connecting the smaller set to the biggest set. We are just connecting either one, either way. It doesn't really matter. You can probably see how this might result in worse runtime though, because we're connecting in some cases at least, the bigger set to the smaller set. Now, if we want to look up what the face of 2 is, we have to travel through 3 to 4 to 1. Right? It's not the most efficient way to do this. So basically, our connect operations are going to be a little faster because we just have to go to the face of a set and connect the two faces, but our actual find operations are going to be really slow. You could imagine a situation in which you have to travel through every single node, right, to get to the face because of this suboptimal unioning, which means that we would have to travel through all n nodes to get to the face of something, so it is connected, could take n time. Imagine in this case, if we wanted to check if 3 and 2 are connected, we'd have to go from 3 all the way up to 1, from 3 all the way up to 1. That's most of the elements right here. And our connected, it's better than it is in QuickFind, but actually asymptotically, it's the same because you can still come up with that same worst case, right? Imagine if we had imagine if 0, for example, was not connected to 1, and now we want to connect 0 and 2. Well, we'd have to start at 2 and go all the way up through basically all of the elements to find out its face is 1, and then we can make that connection. The connection itself takes constant time, right? Because we're just drawing one arrow between two elements, but in order to figure out which two elements we actually want to connect, we might have to follow up this linear length path of things, which would take n time. The thing to note here is even though these two connects are both upper bounded by linear time, this one is less efficient. On average, this one will take more time, right, than this one. You could imagine that if you have to rebind every parent, which is why this one's taking n time, generally that's going to take longer than if you just have to search for given parents. But that comes down to an implementation specific thing, and we don't need to worry about it. for the purpose of asymptotics. Okay, so the weighted quick union. The weighted quick union is, of course, the same thing as a quick union, except we are always connecting the smaller set beneath the bigger set. What is the runtime of that? We're not going to prove this in this class, but it actually improves it from O of n to O of n log n. Same thing with is connected. I'll give you a little bit of rationale for why that is the case. And basically what it is that if you always connect the smaller set to the bigger set, right, you're going to end up with a kind of bushy tree. You're going to end up with something that looks more like this, right, as opposed to a spindly tree, which might look something like this, which is what you might get if you do not connect them based off weights. This takes n time to traverse, and this takes log n time to traverse. Log n time basically means that you're halving something every time. And you can see here that we can access half of the elements, right, every time we go down a layer, basically. So that's basically a little bit of rationale in it. Don't super worry about proving that, though. You don't have to. You can take, later classes like 170 or something if you really want to prove it. I don't think they even teach this in 170 anymore, so maybe not. But that's basically this problem. I know this one ended up being really long and conceptually heavy, but again, everything you need to know about weighted quick unions is here. So if you can do this problem and you can answer the runtime problems, you pretty much have it. So I hope this was helpful.